Hello everyone, welcome to another class. I'll be taking Dispersion of Light at this time, and I expect that you pay rapt attention. I'm not going to be super loud, so I expect that you listen attentively and pay rapt attention. Okay, let's have a deep dive. Dispersion of light. So I'm going to start by defining dispersion of light to be the splitting. Specifically, I'll say dispersion on its own is the splitting or decomposition of a beam of white light into its constituent colors called spectra. It is a term relating to the variation of refractive index with the wavelength. So we can see dispersion of light is therefore accompanied by change in speed colors, wavelength, and refractive indices. But note, all colors of light travel with the same speed in a vacuum. So there is something called normal dispersion. For normal dispersion, which happens through most transparent, substances like glass. The refractive index here increases as the wavelength decreases. That is, the dispersion is directly proportional to so just keep this one in mind. I might have to use it later, but just keep the formula in mind. So another concept is for anomalous dispersion. There is a rapid change in the refractive index with the wavelength of the neighborhood. Assumption. With a shorter wavelength at a lower refractive index. So in this case, in anomalous dispersion, the refractive index varies directly with the wavelength. So just keep that in mind. Those are important points. Yeah. So there is another subtopic called dispersion of white light. We're going to look at something interesting now by a triangular prism. And this produces the spectrum of white light. This is an important part in physics. So listen attentively to the explanation first before I now give you one of the common things that you know. With a narrow beam of white light incident on a prism, a spectrum consisting of red, orange, yellow, green, blue, indigo, and violet, popular Roy beef, is produced on the screen. See the idea here. You have a prism sending white light as the incident ray to the normal. This is white light. It now breaks into 7. Coming. A minute. Bends, then produces emergent. Red emerges first. From that same white light, another one bends, from which orange emerges. That same white light, another one bends, from which yellow emerges. From that same white light, another one bends, from which green emerges. That same white light, another one bends, from which blue emerges. From that same white light, another one bends, and bends again. You know, at the end, at the emergent ray section, they're always bending again, right? You know, they still bend there. It's not like they just move and move out, no. So just keep that in mind. I'm gonna erase that now, but I wanted you to know that they're bending. So you're not just drawing a straight line from here. Just no, that's not what you're doing. So because it bends again at all these points, it bends again. So keep that in mind. So from that one, another one emerges, and this time around it's indigo. From that same white light, another one emerges and bends again. That's the final violet. So the idea is that just from white light, you have, all of this produced, and this is called the spectrum of white light. Now, quickly let you understand. It's similar to the colors of the rainbow, and also when you write it like this, Roy, as you are going from left to right, it has wavelength decreasing and frequency increasing. So the idea is that in many multiple choice questions, you see which of them has the longest wavelength. Since wavelength is reducing in this direction, it means that red has the longest because it is decreasing like this. That means this guy will have, I can say violet, this one, red has the longest wavelength, while violet has the shortest wavelength. Then you can easily interpret that, between red and orange and yellow now, the one that will have the longest wavelength is red. But between orange and yellow, you know that orange will have it. Between yellow and green, yellow will have the longest. So it keeps reducing as we go like this. So same thing for frequency. As we go like this, frequency is increasing. So if it is increasing, it means that red has the shortest frequency because it is increasing from left to right. And that means also that violet would have the highest frequency. I can call frequency smallest. In this case, not shortest, smallest frequency. So just keep that in mind. Just keep this particular one, Roy beef. As you write it, as you're increasing it from right to left to right, wavelength is decreasing, frequency is increasing. So in case there's a OBJ now that talks about these three and asks you which of them has the highest frequency, because frequency is increasing like this, we know that it's blue. You understand? And if a OBJ talks about the three now, say between yellow, green, and blue, which of them has the lowest wavelength? Because we know that wavelength is decreasing from left to right. We know that the lowest wavelength will also be blue. So blue has the highest frequency and lowest wavelength among those three. So that's just the idea. I hope you get it. Yes. So we'll move from there now on the idea of this to straight into there's something called chromatic aberration. Let me talk about that. Chromatic no, let me talk about some things before that. Uh, hold on. Okay. So let's see. You can see with hydrogen light, We have already established that for normal dispersion, don't forget for normal dispersion, we've written already that D is directly proportional to N, then change in V over V. It's good to note that among all those colors, red has the fastest speed. It comes out first, of course, and so speed is also reducing from left to, let me add that speed, let me also add it, speed is decreasing too in that direction. See it from left to right, its speed is decreasing. So take note of that too, because red comes out first, and red is the least deviated. You see others, when it comes to others, as they come out, they are bending the more. They keep bending more, bending more. So red is least deviated. Red has the fastest speed and is least deviated. So also the deviation increases from, so the deviation also increases as frequency is increasing too. Yeah, you can also write too, deviation is increasing. So deviation increases from left to right too. Because red bends less than, so orange bends more than red, yellow bends more than, so as you're going from left to right, deviation is increasing. So give you like 4 things now that you can easily use to answer questions. As you know, Roy give, you can just use those 4 things to answer questions. So note that. And since deviation is inversely proportional to, let's say it, let me put this, there's something missing here. Let me write it in black. Lambda, from what we've written before, over here, for normal derivation, see it right here. So since red is directly proportional to, since deviation is directly proportional, not deviation, dispersion rather, is directly proportional to this entire thing. Okay, I'm not going to make that point now. Just keep this formula in mind. Keep this formula in mind. Whatever point we want to make, we'll make it while we're using that formula to solve questions. As if we do. But notwithstanding, I've established it and it's a good point. So it's like saying the dispersion depends on refractive index, speed, wavelength. This is change in speed. This is speed itself. This is refractive index. And of course, you know what lambda is, wavelength. So now let's keep saying what we are saying. Let's keep making notes. Hydrogen light. Not yeah, let's say hydrogen light. Hydrogen light. Or I can say in the front, with hydrogen light, lines of all colors are produced. With mercury light, what we mean that are produced is when we run it through this place. No, this is like running white light now. If we use hydrogen light, you have lines of all colors being produced. That's we're talking about instead of white light. So if we run hydrogen light, lines of all colors are produced. If we run mercury light, blue and green lines are produced. Why, if we run sodium, yellow line is produced. So we can define something called angular dispersion. Let's define that. Angular dispersion. Or we can say dispersive power. Angular dispersion or dispersive power is the rate at which the angle of refraction or diffraction changes with the wavelength. Keep that in mind. So it's a very important point. So another name for it, it's also called, it is also called angular difference. Between the deviations produced by any two colors. And the formula for that is the theta by the lambda. So that's for angular. Let's talk about linear now. Linear dispersion. The linear separation of two lines in a spectrum by unit difference of wavelength the lambda is called linear dispersion. So we see that clearly angular dispersion is this, linear dispersion is this. So take note of that. Oh, if I want to relate the two, I'll write it like this. So the relationship between the two, can say generally the L, the lambda equal to F, the theta, the lambda, where F is focal length of the lens used to project it onto a screen. So keep that in mind. So right after that, we are going into something called chromatic aberration. Just talk about it. This is the image defect. Having blood and colored images when white light is incident on a lens or dispersion of a narrow angle prism. So the image defect of having blood and colored when light is incident on a lens, or it is caused by the dispersion. So there are two causes: when light is incident on a lens, or by the dispersion of a narrow angle prism. So it is corrected let's use something called chromatic doublet. Double lenses. So the chromatic doublet or double lenses. So another subtopic immediately, or another, subtopic: dispersion of sound wave in gas. Variation of velocity with frequency. We know that V no, generally we know that V equal to F lambda. This is the normal thing. So a variation of velocity with frequency like this one now, is abnormal. Because normally this relationship is direct relationship, and this one is showing what? Inverse or abnormal. Let's put inverse or abnormal. This kind of relationship describes an anomalous absorption of sound. And it is why at high frequency gases are completely opaque to sound waves. Now, let's see. So we have already showed how to produce a pure spectrum. You use the prism, you pass white light through it, and then But then let's talk about how to recombine those colors. After producing them, recombination of the colors. Okay, excuse me. What we talked about is producing the spectrum of white light. Let's now talk about something called the pure spectrum. That's quite different. So let me make that point. What we talked about above, when we talked about all of these things here, is like producing spectrum of white light. So, but let's talk about pure spectrum now. We'll call this subheading the production of pure spectrum. And I will write a lot of notes here. For the production of pure spectrum, a pure spectrum contains monochromatic. Let me just take the entirety to the next line. Monochromatic images only. So, and it says overlapping. I'm just going to write it. Overlapping of images can be eliminated if a narrow white light is used. If the incident beam is parallel to the prism. Around for a bit. Then, if the prism is 60-degree prism or is placed in position of minimum deviation. And in order to get a pure spectrum, to get a pure spectrum from a prism, to get a pure spectrum, let me write, to get a pure spectrum from a prism, a triangular one at that, we use lenses before and after the prism. We use something called the spectrometer. Sorry, think I almost got distracted there, so a spectrometer is used, consisting of a collimator, table, and telescope. So please work hard. You see, I canceled my distraction by saying not be me and you. I was like, okay, I'm not gonna, leave the work I'm doing and focus on something else. So, yeah, that was just what you had there. Pinpoint focus. So telescope, yeah. Then let's quickly talk about recombination of colors, how that is done, especially when you are forming pure spectrum. I will assure you in science, for you to pass, for you to excel and work hard, things don't have to be interesting. You just have to work on them. So not about your interest. It's not about your mood. It's about hard work. The combination of colors. When you combine the colors into white, you can do that. Okay, colors can be combined. Let me do that. The colors can be recombined into white by using inverting prism, Newton's color discs, and you can also use plane mirror. And let's go to another subheading, colors of objects. Point I want to make here is that color presented to the eye is the color of light. It reflects in white light. So color presented to the eye is the color of the light it reflects in white light. So just get that point. Whatever you see is a reflection of that particular thing in white light. So if I see black, that's like black on white. Black on white. I did not say black and white. So if I see maybe red now, I'm just seeing that red because the natural light everywhere is white. That tells you something about what is expected of our life: purity, cleanliness, white light. So whatever you see on that is just a reflection of that particular thing on white. An object appears white if all colors of white light are reflected. That is, if anywhere you see a combination of red, orange, green, blue, indigo, and violet all together, what you see at the end of the day is white. So, but the idea here is that now the object appears colored if some colors, out of rugby, some colors are reflected and some are absorbed. When nothing is reflected at all, when there is no reflection, we see black. Or we say object appears black. So you see the idea here. When there is reflection of all the colors of rugby, you see white. when some reflect more than the other, you see, you see some colors that you see. And later on, you will see what we can have when you combine colors like red and red and blue together. You see what the results in. We'll talk about that. But when there's no reflection at all, you see black. No reflection, black. It is colored if some reflect and others are absorbed. When all reflect and all colors are reflect, we see white. So let's get the idea. Let's talk about color or light filters. Uses of color filters. Color filters. Some people call them light filters. Light filters. So number one, they're used for analysis of colors in transmitted light. So that is to know which color is absorbed and which color is reflected. To know colors absorbed and reflected and the ones reflected. The other use is for observing the appearance of colored objects in colored light. Observing the appearance of colored objects in colored light. So let's now talk about classification of colors, which has been one of the interesting parts we're getting to. Classification of colors. So we can classify them into primary, secondary, and complementary colors. Or we classify them into colors of light and colors of pigment or paint. So let's talk about them. Let's talk about primary colors. Primary colors. So these are colors combined to form others. So they're like the fundamental. That is, you can use an example of those colors are red, blue, and green. Primary colors are the ones that are combined to form others, e.g., red, blue, and green. So primary colors are red, blue, and green in light. And you can have red, blue, and yellow in pigment. That's a different level. So, but the common one, you already know red, blue, and green. You can choose to stop there when you're defining. But when you want to talk about pigments, you mention red, blue. The primary colors there are red, blue, and yellow. So, secondary colors. These are colors produced from combination of two primary colors. Example is cyan. You get cyan by combining blue plus green. You have magenta. Please, these ones are important OBJ questions. They can even be asked in theory. Red plus blue gives you magenta. Yellow comes from red plus green. So you can get light and orange. Sorry, you can get orange rather. Orange comes from red and yellow. Green comes from blue and yellow. Purple comes from purple or violet, comes from red and blue in paint. So this one, take note of the fact that this is an exception. It's in paint. So normally the answer for red and blue is magenta, but in paint you have purple or violet. Just keep that in mind. There's something now called another subtopic called color mixing. And that's what we just did right here. So this kind of color mixing we did here is called, so the combination of colors to produce another entirely different one, another entirely different color. So the combination of colors to produce another entirely different color is color mixing, and it can happen by addition. Give me a minute, let me catch a breath. So when it happens by addition like that, when it happens by addition, it is called additive mixing. So now the idea is so that color filters that we mentioned. So let's take note of the fact that it transmits its own color, but absorbs any color that falls on it. So note, it transmits, it is made out of colored glass, made out of colored glass, and transmits its own color. While absorbing Any other color? So transmit to some color and absorb any other color. Keep that in mind. So while we spoke about the classifications, I should have also talked about I think we have talked about colors of light. Can talk about color pigment. But right now we're talking about additive mixing. That's a good idea. Yeah, let's not mention anything about subtractive mixing. This mixing that you see above is called additive mixing. Keep that in mind. I will not be talking about anything with subtractive mixing yet until I talk about colored pigment. Colored pigment has to do with the substance which gives an object its color. It's called a pigment. A pigment absorbs all colors except its own, which it reflects. So it reflects its own color. We already know that we said something similar to this before. Black pigment, when you talk about black, no reflection occurs, no absorption, nothing. Absorbs all colors. Absorption occurs, absorbs all colors. So black absorbs all colors and reflects none. No reflection occurs for black. White pigment reflects all. The mixing of color pigment. Now this is where we talk about subtractive mixing before we move to the next thing. The mixing of color pigment is called subtractive mixing. So that's where subtractive mixing comes in. So very important. When I go to the latter part of this lecture, here I will mention the electromagnetic spectrum. This one is a very important topic, electromagnetic spectrum. So the electromagnetic spectrum is made up of seven kinds of rays. This comprises I'm going to write them as RMI VUXI. Don't ever forget that acronym. This is radio waves. That's what it stands for. This is microwaves. This is infrared radiation. This one is visible light. This one is ultraviolet. Ultraviolet radiation. This one is X-rays. And this Y is stands for gamma rays. Just know. So RMI VUXI like this, just almost similar to like beef. When you want to know most of the features, as it goes from left to right, it has wavelength is decreasing. What does that tell you about if wavelength is decreasing? It means this guy has the highest wavelength because it's going down, it's decreasing. Then also frequency is increasing. Same principle applies. So if frequency is increasing, this guy has the highest frequency, right? So that's how it works. So just keep these 2 points in mind, and also keep that acronym RMI VUXI. You'll be able to remember these things. And so as frequency increases penetrating power too. So penetrating power is increasing. So definitely this guy has the highest, gamma ray has the highest penetrating power, while this one has lowest. You understand? Lowest, highest will be here because it's increasing. So it goes higher. So, but for something that is decreasing, that means this guy has the highest. Something that is decreasing, this guy has the highest, and gamma will have the lowest. So just keep some of those principles in mind. Let's now talk about the sources, detection, and uses of this electromagnetic spectrum. Number one, let's talk about it backwards. Gamma rays. Gamma rays sources. Let me just put it there way for me to put. Okay, let me just say sources. You get it from nucleus of radioactive atoms or materials from their nucleus. And you can detect the detection. You use Muller tube or photographic plate by ionization effect. Keep these things in mind. That is then the uses, gamma ray uses. It is used for treatment of diseases in medicine. Diseases like cancer. So that's what gamma rays is for. X-rays, the sources include bombardment. You can get it by bombardment of heavy atoms by fast moving electrons. So when you bombard heavy atom with fast moving electrons, you produce X-rays. The detection, how do you detect it? Use photographic plate or fluorescent screen. Take note of that. Then the uses of X-rays can be used as tracers in medicine and industry. Can be used as tracers, not traces, tracers. Tracers in medicine industry. There's still more. In medicine industry, let me move it. Medicine industry, scientific research, yeah. Agriculture too. Ultraviolet. Ultraviolet, the sources. All hot bodies give you ultraviolet. Your body right now, even the human body, give ultraviolet rays. Then, example, discharge tubes. That's the discharge tubes. Like mercury vapor. Solar radiation. So the one from the sun is ultraviolet. etc. So the detection, you detect it, luminous objects. So e.g., you use luminous paint and detect it. Any luminous object, most of the objects are luminous paint, photographic plate. I mean, most of these objects we mentioned right now. Photographic plate, fluorescence, photocells, skin. So the use is rather used for treatment of skin disease. Treatment of skin disease as it affects the skin and kills certain bacteria. So that's the use of ultraviolet. Still have more. We have visible light. The source of that, hot bodies like the sun. So the light that you see from the sun is called visible light. Why the radiation from it is ultraviolet, solar radiation. So that light is sun. You see visible light from flames too, and even sometimes in discharge tubes. The detection is by photographic plate, since it is visible to the eyes. Visible light helps your sense of vision, helps you to see. So that's the use. Infrared. Infrared, the source is all bodies too. So for detection, take note of these things I'm mentioning. For infrared rays, phototransistor, thermocouple, or thermofoil, bolometer, and special photographic plate. So infrared rays are used in telecommunication. Or let me put in the front, wireless. They're used in greenhouse effect. So wireless telecommunication, greenhouse, global warming, and infrared helps photography at night. You see that some of the movies you watch when the police wants to conduct an operation at night, they use one red light like that. That's infrared photography at night, or should I say night vision. Next one, radio waves. And the sources, the transmitter, straightforward. And then it has to be, the detection has to be a radio receiver. Then they use. So take note of that. So, yeah. So this idea of calling something spectra, note. Okay, let me even just define it. Spectra is the display colors when atoms or molecules of matter are excited due to inelastic collision with electrons. Energetic molecules or photons. So let's talk about the classification of spectra. There is solar spectra, this is spectra by glass dispersion. There is atomic spectra, the electrical discharge. in gases, low pressure. Due to electrical discharge in gases at low pressure and high voltage and energy levels in an atom. Take note of that. I'm going to read it later. So I can also talk about another one called okay. We've talked about solar atomic. So let's do okay. Before I go, let me quickly do a difference between emission. This is a common exam question. Difference between emission spectrum and absorption spectrum. Common exam question. Spectra. This is spectra from direct or luminous source. This is spectra from a source. Let me write that way. From a source interposed by an absorbing medium. Spectra. The emission spectra is a spectra with, let me put it, with emitted light or discharge and wavelength. This one is with given light from a source certain passing through the gas. With certain wavelength absorbed. Third one is, in this case, bright lines on dark background. And here, dark lines on bright background. I believe that was 3, and this is 4. This one is directly observable with a spectrometer, while this other one is not directly observable with a spectrometer. So it's not directly observable there. So let's take note that when you talk of emission or absorption spectra, they can be range spectra, band spectra, or continuous. So I will give you, go and look into this as an assignment. Go and look at the explanation of each of them. So when next we meet, would continue to solve problems. See you in the next class.